All right, welcome to Chapter 7, Section 1, called Bisectors of a Triangle. So just a couple things. Oh, this is for Integrated Math 2 or IM 2. So a couple things just to go over the front screen here. You should see a due date on your student side. I know it's not on my teacher screen here, but you'll see it on your side. You also have attempts here. You always have unlimited attempts on your homework, tests, and quizzes. So you can come in and try them as many times as you would like. Number of questions just tells you how many are in this particular assignment. Grading policy is best score, so whichever attempt is the best one is one you keep. Partial credit is always enabled, so if you answer one of 3 questions correctly, you get credit for the one question, or however many you answered correctly. Down here it says once you start your homework, you must finish it before you can work on anything else. What that means is once I click start, down in the bottom right corner, there will be a submit assignment button. I need to make sure that I click that submit assignment button no matter what when I want to leave this screen. For 2 reasons. Number 1, it's going to lock you out of all of your other assignments if you don't click that submit assignment button, just like it said on that first screen. It's going to assume you want to leave this attempt open. Remember, you have unlimited attempts, so you can definitely click that button and come back in and try again. As long as you have a green check mark on anything that you've tried, you will not have to repeat that one. So if you haven't tried one, or if you've gotten it incorrect, that's the ones you'll have to try again. The other thing it does is it actually updates the grade book so that your teacher can see what you've been working on. Until you click submit assignment, basically your account's paused in that assignment. We can't see what you've been working on. So good habit, always click on that button. On the side here we have a calculator, which is sometimes open, it's not always open. And then we also have explanation, example, and message center. So explanation will tell you you're going to lose your question attempt because it's going to give you the answer to this question. So definitely, it's not going to give you the answer and then let you come type it in. That's not how that works. The example, though, will show you an example of this same problem type so that we can work through this problem. And then, you can look through, see exactly what it is. We have a background here. We have the circumcenter theorem that we need to know about. We also need to know what a perpendicular bisector is in order to do this. So I'll talk about this in just a second. As we go through, and then it shows you how to work out and what to type in here. Once you're done, you can click X. You can click on another example to see another one if you'd like. You can also message your teacher directly from the screen so that it'll attach a picture and we know where to come help you. All right, so let's go ahead and take a look at this guy. So we have consider this triangle here, TUV. It says the perpendicular bisectors of its sides are AD, BD, and CD. They meet at a single point D in the center. In other words, D is the circumcenter of TUV. So it's the place at which all of the perpendicular bisectors meet. We call that the circumcenter. So it's just got a special name there. And then it gives us some other information here. So first, what I'm going to do is I'm actually going to copy this little diagram so I can start drawing on it. Just a little bit here, and I'll give myself some room too because I'm going to need you know what, I'm going to actually give myself a little bit more room than that because we're going to have to work a few things out here. So, although my program is very neat, it doesn't give me a whole lot of room to work things out if I just copy the diagram. So I want to give myself a little bit extra room there so that I can work out the math here. Okay, so let's go ahead and take a look at the things that it just told us. So I have AD. That's a perpendicular bisector, and we're going to talk about what perpendicular bisector means in just a moment. BD is also a perpendicular bisector, and CD is perpendicular bisector. So we can see that they're meeting here in the center. So perpendicular bisector, what that literally means is it's, number 1, it's perpendicular. We hear that in the name. So we can even see this little perpendicular mark. It means that it's at a right angle to this side that it's coming from. Bisector means that it's cutting that side in half. So it means that all of these are equal to each other. So AT is equal to AV, BV is equal to BU, and CU is equal to CT. So immediately I can see it's cutting a whole bunch of things in half. That's what perpendicular bisector means. It's perpendicular to the line and it's cutting it in half. The other thing a perpendicular bisector does, this is another piece of perpendicular bisector, is that it's equidistant from this point to the end here. So these lines are also equidistant or equal to each other. So I'm going to use 4 here, like this. So TD would be equal to DV. Well, DV would be equal to DU, which means that it's also equal to TD, right? So we can actually see very quickly that they're equal all the way around. Oh, that should be 4 of them, sorry. I meant to mark 4. 1, 2, 3, 4, like that. So we can see that these lines are equal, and I'm even going to make them red so they stand out a bunch. So all of a sudden, these guys are equal to each other all the way around. So this is actually the circumcenter theorem, is that if we have 3 perpendicular bisectors drawn in a triangle, then from the circumcenter, this line from the vertex is equidistant from the circumcenter. And it's because of what the perpendicular bisector does. That's part of the definition of perpendicular bisector as well, but that's the circumcenter theorem, that it immediately does this, where these 3 lines are equal to each other. All right, so now that we've covered those 2 pieces, let's go ahead and look at the given information. So it says CD is 36. Oops, turn my line tool off there. So this is 36. BV, so this guy up here, just BV right here, is 58. And UD, so this one going down here, is 60. Well, immediately, if UD is 60, all of my red lines are 60. All of these coming from the circumcenter to a vertice are 60 degrees. So I know that immediately, which is actually one of the questions here. They ask what VD is. Well, I know that's 60 already. They don't ask me what DT or TD, whichever way they want to list that. But they do ask me what some of the other pieces are. So I'm going to end up having to use Pythagorean theorem here because I have a lot of right triangles. So anytime I have right triangles, I can use Pythagorean theorem to fill in a missing piece of that triangle. As long as I have 2 of the lengths, I can fill in the 3rd one. So they're asking me what UV is. So they want this entire side, UV. Well, I know what part of it is. So I actually don't even have to use Pythagorean theorem on this one because remember, perpendicular bisector, it cut this in half. If this side's 58, this side is also 58. And if I want the entire thing, we can do segment addition, and I can just say 58 plus 58. And that gets me 16 and 11. So 116. So I don't have to do Pythagorean theorem there. So let's see. Let's look at TC. So now I'm going to look at TC, which is over here. So I don't know anything about UC on this one. I didn't get any information on that. But I do have this side of the triangle and I have this side of the triangle. So I am going to use Pythagorean theorem here. So remember, Pythagorean theorem is a squared plus b squared equals c squared. And we haven't used this in a while. It's probably been a few months since we've actually used Pythagorean theorem in IM2. So it's just one of those things that, a lot of this math is cumulative, meaning that eventually we end up using it again or we kind of just keep building on it. But it doesn't necessarily go away. We might not use it for a little while, but we always end up kind of coming back to it. So it's definitely important, even if something seems a little small at the time, we end up using it again in the future to build on more pieces. So with this one, A and B, these are the legs of my right triangle, and this is the hypotenuse. Hypotenuse. Oops, that looked really ugly, sorry. Hypotenuse. So the hypotenuse is always across from the 90. So I just carried this 90 over to the other side, because if this is perpendicular on this side, it's perpendicular on the other side. So we have 60 is my hypotenuse, so it's going to be 60 squared. A and B do not matter which one is A and which one is B. They're just the legs of the triangle, the ones that create the 90 degrees. So I'll just go ahead and say this is my A, and my B is going to be down here, what I'm looking for. So A is 36, And b, I'm just going to leave b squared for now. So I'm going to go ahead and use my calculator for this. So I have 36 squared, oh, it doesn't look like I have a square button, equals 1,296 plus b squared equals 60 squared. Ooh, is that correct? 60 squared? Nope, that wasn't correct. I was going to say that looked like a really large number there. So 3,600. I'm going to subtract the 1,296. So, sorry, 1,296, I should say correctly. Boop. And so these guys cancel, and I have b squared equals, I'm going to come over here and go minus 1,296. That gets me 2,304. And so at this point, I want to know what just b is, not b squared, so I'm going to take the square root. So b is square root 48. So this length here that I'm looking for has to be 48. So I can go 48 and check. Yay! All right. So let's see, we're going to go to the next theorem here. So let me clear this guy out and get some more room here. So I'm going to take a picture of this triangle real quick. And let's see. Come on, where's the picture? Oh, was this it? Oh, that was it. Sorry, I didn't notice it saved down there. Alrighty. Let's zoom in a little bit on that guy. Okay, so now we have the angle bisectors of triangle XYZ, or XG, YG, and ZG, and they meet at a single point G. In other words, G is the incenter of XYZ. So when we have the perpendicular bisectors, we call that the circumcenter. When we have the angle bisectors, we call that the incenter. Very, very similar names. So it's one of those things, it can definitely be a little confusing because we have some very similar type names here. So if we're looking here, and I'm going to go ahead and highlight these guys. So I have the angle bisectors are XG. And I think I'm going to change my color here just so that they're a little bit more obvious. So I have XG and YG and ZG. So I have some angle bisectors. So remember, it's angle and it's bisecting. So what does that mean it's doing? It's cutting the angle in half. So if XG is an angle bisector, that means that it's cutting this angle in half. So I have half the angle here. I also have half the angle on this one and half the angle on this one. Oh, I need a third one there. So, and I'm just marking it 1 to 1, 2 to 2, 3 to 3. So remember, that's how we mark congruencies on there, is we use the number of arcs or number of tick marks. So far, this is what we have. The incenter, what it does is it's kind of the opposite of the circumcenter. So in the circumcenter, we had the perpendicular bisectors, and that made these segments that we just highlighted blue, that made them congruent all the way around. Well, when we have the incenter, when it's the angle bisectors that meet at a single point, it makes the perpendicular lines, and they're not perpendicular bisectors this time, they're just perpendicular lines from the incenter to the side. Those are the congruent marks on this one. So, or not congruent marks, but congruent segments. So it makes these perpendicular segments congruent all the way around. So it's kind of they're very similar pieces, but they react differently. So perpendicular bisector, circumcenter, and that makes the segment from the vertice to the center congruent. Angle bisectors make the perpendicular segment from the center to the side congruent. So I don't know if that really helped me saying it again. I know it's all very similar, but this is the diagram that goes with it here. This definitely hopefully helps you see the pieces here. So I know that these are all congruent to each other because they come from the in-center. And then we have some given information here, so I'm going to go ahead and fill them in with green. Why not? So we have DG equals 12. Well, if DG equals 12, GE equals 12, and GF equals 12. I'm just going to fill those in. I already know those three. And actually, that's one of the pieces they asked me here is EG. So I can immediately put 12 on that one. I already know that one. ZG, so ZG, this longer one, equals 17. And then they also give me DYE, so this whole angle at the top equals 42, and I'm doing this really dramatic, weird, big thing, so you know it's the whole thing. And then FGX, so this piece here equals 56, like that. So FGX. Sorry, FXG, it would help if I was writing the right spot. FXG, it's down here, 56. I'm glad I caught that, because that would have kind of complicated things a little bit here. All right, so now I've gotten my given information filled in, and they're asking me for two more angles. So they're asking me for FXD, this whole angle here. Well, remember it was an angle bisector. If I know half of it, the other half is the same, and all I have to do is add those together. 56 plus 56 equals 12 and, not 10, 11. Got to do my carryover. So this whole thing is 112. And then they're also asking me to find FZG, so this angle here. And one thing, I know it can be a little difficult to kind of separate out when you're looking at this, but I have a triangle. I have this whole triangle. I have the top, I have the left, they're asking me for the right. The three angles of a triangle add up to 180 degrees. So if I know I have 42 and I have 112 on the end, on the left here, then whatever this entire angle is, I'm just going to label it X for now, is going to be what's left over from 180. Well, why do I care about that? Because I don't care about the entire angle, right? But remember, angle bisector, if I know what the entire angle is, I can divide by 2 to get back to this half of the angle. So it's just one of those things about paying attention to what do we already know about the triangles. And even though, yes, it's kind of complicated looking inside of here, we can still use that basic idea of the angles of a triangle add up to 180. So let's see, we have 4, 5, and 1. So 154 plus x equals 180. We're going to subtract from 154. Sorry, from 180, 154 from 180. So we end up with x equals, we have to borrow, and we end up with 6 and 2. So we only end up with 26 degrees left for the entire angle. Remember, there are 2 of them there. I only want half of that angle. So I'm going to divide 26 by 2, and I get 13. So this is only a 13 degree angle. All right, let's check and make sure I did all my math right there. Yay! All right, so we're going to look at one more piece here. And this is just going to be a theorem based on these guys. So taking some of these kind of complicated pieces here and moving them into a theorem, or a proof, sorry, not a theorem. I'm just losing my wording here after doing so many of these. Okay, so I went ahead and I copied my diagram. If you don't have a picture of this diagram, which every time we start these, it's a new one. So definitely copy this down on your page so that you can start marking up your diagram as you need to. So what we're doing is we're proving the theorem. If a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. We're proving that. So I know we've already been given it because we talked about that in number 1, but now we're going to prove why this happens. So what they're telling us, they're giving us that PX is the perpendicular bisector of YZ. So I'm going to have to define what does perpendicular bisector mean. It means two things. It means it's perpendicular. So we have two angles equal to each other here. They're both 90 degrees. And then it also means that it's bisecting. I'm going to have to define that. I'm going to have to state these things. So first I need to send this to proof. And then I'm going to define those two pieces. So before I jump into that, I like to kind of have my game plan. So I'll define those two pieces. And then what we're going to do, because we can't immediately start saying that it's equidistant from the endpoints and saying these guys are equal to each other. We don't know that yet. What we're going to do is we want to prove that these two pieces are equal. And if we're thinking of a triangle like this, because we've been working with triangles, oh my gosh, so much in the last couple of weeks. That's pretty much exclusively what we've been working on. We can prove that the two triangles are equal to each other. Once we prove the two triangles are equal to each other, then we can prove that corresponding parts of congruent triangles are equal. So if we're looking at the blue triangle and the red triangle here, we already have side angle. Side angle. And remember, we have those four pieces. We can do side angle side, side side side, angle side angle, or angle angle side. Those are our four ways to prove triangles congruent. If those don't sound familiar, definitely go back to chapter 6. We went over those really, really heavily. I believe it was section 3 and section 4. Also in section 5, we were covering them again. So we went over those quite a few times in chapter 6. If those don't sound familiar, definitely go back and watch those again. They should sound very familiar at this point. Or if not, definitely identifiable. So we want to prove something else congruent. I'm either going to need an angle because I have side angle. So I'm either going to have angle side angle, or I'm going to prove the next side congruent. So that I can use one of those pieces, because it has to follow one of those progressions. I can't do angle, angle, side. Well, I could. If I could prove something about this angle, I could go angle, angle, side. Or side, side, side. I only have one side to start with, so more than likely I'm not going to prove something about the other two sides. Maybe one of them, but not both of them. In fact, one of the sides is the ones I want to prove, so it's not going to be side, side, side. Looking at this, I can't prove anything about these angles out here. Not really. Not yet, anyway. I can't prove anything about this angle up here either. There's nothing I can prove about it. But there is something I can prove about this shared segment. The fact that they share it means that it is equal to itself. So that's going to be my congruent side. So now I have side, angle, side. So now I know that the blue triangle is congruent to the red triangle. And I can go ahead and state that corresponding parts of congruent triangles are congruent. All right, so now I've gone through and made my game plan. Let's go ahead and fill this out, and we'll kind of walk back through it again. So I already sent this piece to proof. We need to explain what this actually means. So I know that angle, let's see, I need to put angle, YXP is, let's see, is a right angle. And the reason for that is it's the definition of perpendicular. Okay. And then I'm going to do the same thing for this other side. So ZXP. So ZXP is also a right angle for the same exact reason it's definition of perpendicular. So now that I know that they're both right, I actually still have to state that they're equal to each other, because even though, yes, they're both right, I haven't actually put those together yet. So YXP is equal or congruent to angle ZXP, and that's because all right angles are congruent. So all right angles are congruent. So once I know that there's two angles that are right, they are equal to each other. So I can go ahead and validate that. So now I have these angles. That's all I've done. Those last 3 steps were just to show that these two angles were congruent to each other. Now I get to deal with the bisector part of perpendicular bisector. So now I can go with x, z, and I think I need to, you know what? They don't have the lines over. I'm going to go ahead and do segment. XZ is congruent to segment YX. And I don't know if it's going to like the lines. It had the segments over the top of this one, but it doesn't have the segments over the top of this one. So it's kind of interesting. So my reason for that is I'm defining perpendicular bisector. So I'm going to validate. Perfect. It accepted that. So it's perfectly fine there. So now I have angle and side. I need to do this last side. So I have XP, darn it, XP is congruent to XP. And the reason for that is it's just a reflex. Anything is equal to itself, but I have to state it in the proof so that I have that side angle side. Now I can say that the triangles are congruent to each other, so I'm going to say triangle YXP is congruent to triangle ZXP, and make sure you're paying attention to the order here. Y and Z are corresponding, X and X are corresponding, P and P are corresponding. So you want to make sure you have them in the right order there. And it's SAS, correspondence. All right, so now I have my triangles congruent. So I can say corresponding parts of congruent triangles are congruent. And I'm trying to think, let's see. I think I have to do this in 2 steps because it goes from congruent to equal. So I'm going to have to do congruent first. YP is congruent to ZP. Oop, and I need to put segment. No. Like that. And I'm going to say CP, CTC, corresponding parts of congruent triangles are congruent. So I'm going to validate. And now I can send this down to be equal. So I know that sounds a little bit funny, but because it's not congruent, I haven't finished. I need to go from congruent to equal. And congruent literally means it's the definition of congruent segments. If they're congruent, they're the same size and shape, they're also equal to each other. So I'm just using that definition of congruent segments to finalize that and click validate, and now I'm done with my proof. So I had to go through and do that, changing it from congruent to equal. That was my last step there. So I can check that, and we are good to go. So that was section 1, and I will see you in section 2.